Modeling dynamical systems normally rely on finding the relationships between state variables. These state variables are commonly defined as a set of compact and complete quantitative variables to describe the system dynamics. Despite the importance of identifying these state variables, it is still unclear how we can find the number of these state variables, what their possible values are, and how they are related, given only high-dimensional observational data. We are researchers from Columbia University. Today, we're going to tell you about our research on discovering state variables hidden in experimental data. Let's first look at an example. Given a single pendulum video shown here, what would you do in order to model this system and hence predict its future behaviors? As in classical mechanics, you may take the pendulum and start to perform force field analysis. You may define the angle theta and angular velocity theta dot as the state variables, measure them from the video streams, and then write down its dynamical equation. Given the initial theta and theta dot, we can roll out this equation in many steps for future predictions. Similar to what we just have done here, numerous successful research of dynamical system modeling derives different numerical methods for writing down the dynamics equation and solving them accurately in lots of highly complex dynamical systems. However, there is always a strong implicit assumption, that is, the observed data streams already correspond to relevant state variables such as angle and angular velocity. This very first step of discovering state variables has been largely ignored and has been taken for granted as input data in dynamical system modeling. If this is still not super clear to you why this problem is super important from the simple pendulum example, let's think about a more complex one here, a fire system. Which state variables shall we start to define? How should we even measure them? We may have lots of knowledge about thermodynamics. Without knowing the state variables, we simply do not know how to relate these first principles to the system we're looking at here. The question that we aim to answer in this work is, given a series of video frames of a swinging pendulum, is there a way to know that only two variables are required to describe its full dynamics? And what these variables might be? Is there an automated process to reduce the vast amount of redundant pixel information into representations in terms of these two state variables? And naturally, we would like this process to work across a variety of physical systems and phenomena. In this paper, we evaluated our approach in 9 simulated and real-world physical systems with video recordings of their dynamical behaviors. These systems include a circular motion system, a reaction diffusion system, a single pendulum, a rigid double pendulum, an elastic double pendulum, a swing stick system, an air dancer, a lava lamp, and a fire system. In the rest of this video, we will first introduce how our approach can identify the minimum number of variables that govern the system dynamics from video frames. We then discuss how we can extract these potential variables with deep neural networks. Finally, we'll present 3 significant properties offered by these discovered state variables for long-term dynamics prediction. The first concept we want to retrieve from the dynamical system is its intrinsic dimension. In general, the intrinsic dimension refers to the minimum number of compact and complete variables needed to fully describe the state of a dynamical system. In a more quantitative way, the intrinsic dimension can be equivalently defined as the dimension of the state space as a manifold in the ambient space. To start with, we formulate the dynamical system as follows. Here, x is the system state, and dt is the discrete time increment. F describes the state evolution from the current system state to the successive state at the next time step. Since our input data is video recordings, and we do not know which variables to measure or how to measure them, we chose video frame as state representation of x. In our first step, we model the function f as a fully convolutional autoencoder neural network that takes in 2 consecutive image frames and predicts the next 2 consecutive frames. As our approach evolves, the function f will be represented in different formats, as we will show later. Remember that our goal is to find the most compact space to implicitly capture the entire system dynamics. Therefore, the autoencoder network will first map the high-dimensional visual observations to a relative low-dimensional embedding, which will then be projected to a high-dimensional image space again to predict the future video frames. If the model can successfully produce accurate future predictions, the low-dimensional bottleneck has to capture sufficient information on the system dynamics. Therefore, to find the intrinsic dimension, one immediate thought is to keep shrinking the size of the latent features until the network cannot make accurate future predictions. However, such methods will require expensive training and validation trials until the prediction is broken. Moreover, in our experiments, we found that such methods already failed to converge when the latent feature dimension is still much higher than the intrinsic dimension. Our key insight is that traditional intrinsic dimension estimation algorithms that utilize geometric structures of the embedding vectors can produce accurate estimation when being applied to our bottleneck latent features. Our solution can automatically discover the intrinsic dimension from the relative low-dimensional latent vectors, and our approach only requires a one-time training setup. Here, we show some results when we applied the Vino-Bicos algorithm. The video frames show the one-time prediction results from our autoencoder network. The intrinsic dimension estimations are based on the latent vector produced by the same network. As summarized in this table, for known systems, our approach produces highly accurate intrinsic dimension estimations. For unknown systems, the ranking of our estimations also makes sense. Our method outperforms direct estimations from raw images. Now that we have identified the number of state variables, we need to find the actual variables themselves. We propose a two-stage framework to retrieve possible state variables from raw video data with neural networks. We hence term our subset of state variables as neural state variables. Our key idea is to break down the identification process into 2 stages. The first stage is to train a dynamics predictive model and identify the intrinsic dimension as indicated in the previous step. Again, this stage uses a latent embedding with relatively low dimensionality, while still being an order of magnitude higher than the intrinsic dimension. The second stage operates directly on this latent embedding to further distill the neural state variables. As shown here, when directly reducing the latent vector during the training of the first stage to the discovered intrinsic dimension, the network cannot converge to a satisfactory prediction. Such optimization difficulty makes this method ineffective in practice. Instead, we propose to train a second autoencoder network that takes in the pre-trained latent embedding and outputs the reconstruction of that input. The special property of this network is that the size of the latent embedding equals the intrinsic dimension obtained from the first step. We find that such a two-stage approach can bypass the optimization challenge and give us a minimum reconstruction error across all of our systems. We can then identify the latent embeddings from this second neural network as the neural state variables. Next, we will demonstrate 3 significant properties offered by these discovered neural state variables for long-term dynamics prediction. Specifically, neural state variables can offer stable long-term predictions, can serve as a novel metric to evaluate the stability of long-term predictions with only visual inputs, and it can produce robust predictions under various visual perturbations. First, let's review what are the possible ways to roll out our existing models for long-term future predictions. With the autoencoder in the first stage of our approach, the latent dimension is about 8,000. we can roll out the model in this space autoregressively as shown here. Of course, we can change the leading dimension to be some other values, for example 64, and follow the same procedure. Similarly, with both autoencoders from our two stages, we can roll out the model in the neural state variable space as shown here, where the neural state variables have the exact dimension as the intrinsic dimension. Predicting long-term dynamics through high-dimensional data has suffered to maintain the ground truth state space due to error accumulation. One repeated observation from past studies is that the long-term predicted sequences become blurred, heavily distorted, or plain background within only a few rollouts. We also observed a similar phenomena in our experiments. This is a very important issue to resolve, because if objects deform or entirely disappear without following the system dynamics, it will be impossible to follow the system evolution faithfully. We define such phenomena as long-term prediction stability. Here, we argue that the first property of the neural state variables is that they can produce stable long-term predictions. But how can we quantitatively evaluate the stability? How do we define at which point the predicted image is so degraded that it does not count as a valid prediction at all? The simple pixel error metric can be misleading for the evaluation of long-term predictions. For example, pixel errors can be smaller for predictions with plain backgrounds than predictions with a slightly inaccurate but clear prediction. This observation further emphasizes the significance of designing an appropriate metric to evaluate stability. Here, we define a metric MS that measures the deviation from a predicted state to the true state space S, and a prediction sequence from any initial state x0 hat. We can quantify the stability of a prediction scheme as the growth rate of the MS as a function of t. For systems for which we have prior knowledge about their conventional state variables, we can extract these physical variables from the corresponding videos through classical computer vision techniques. In this case, the metric M can be readily defined as a binary value indicating whether the same set of physical variables can still be distilled from a predicted state X. Consequently, if the predicted frame is heavily blurred or distorted, we will not be able to distill meaningful physical variables. Thus, M will be 1, otherwise M will be 0. Moreover, to more generally capture the long-term predictive stability of various prediction schemes, M should be evaluated on prediction sequences with multiple initial states. Therefore, we need to calculate M as the reject ratio to indicate how many predicted frames at each time step from different initial states will fail to pass the physical variables extraction test. With the above test, we can quantitatively compare the stability of various long-term prediction schemes. Both the 8000 dim and 64 dim schemes often cannot give stable long-term future predictions, while our predictions through the space of neural state variables constantly produce stable predictions across all systems. Our experiments also suggest that this metric matches the same pattern when using different physical quantities to quantify the stability, such as kinetic and potential energies. Please see our paper for more details. Why is this the case? Inspired by lessons learned from computational physics, an effective fix to the unstable long-term prediction is to construct a prediction scheme where the predicted states will be projected into a small neighborhood of the state space. Here, neural state variables serves as a strong candidate solution. This is because neural state variables have the same dimension as the intrinsic dimension. This fact prevents predictions from falling off the system manifold into new dimensions. We provide a more detailed theoretical analysis in our supplementary materials. Another interesting aspect to notice here is that even though neural state variables provide the most stable predictions across all the systems, they have an inferior performance on one-step prediction accuracy, since neural state variables were obtained by performing reconstruction on the latent embedding from the first network. To combine the best of two worlds, we propose a hybrid prediction scheme as our final solution for long-term prediction. That is, to use neural state variables as stabilizers while performing long-term predictions with their corresponding high-dimensional latent embeddings. For every few rollouts through the relative low-dimensional latent features, such as the 8000 DIM scheme, a one-step prediction is followed over the space of neural state variables. As shown here by the green curve, our hybrid scheme offers both stable and accurate long-term predictions. Here are some qualitative examples. Now let's take a step back and look at the stability metric again. In the above case, we have assumed that the prediction stability can be evaluated by extracting physical variables. Yet, it is common that, in most of the video representations, we know neither which variables to extract nor how to extract them directly from the videos. As noted above, pixel errors are also not reliable. In this case, a very challenging but critical problem is how we can evaluate the long-term prediction stability from videos. Resolving this problem can potentially open up the door to quantitatively evaluate the prediction stability of various schemes for many complex and unknown systems, all directly from videos. Here, we propose the second significant property of neural state variables, that they can serve as the stability indicator for long-term dynamics prediction. Specifically, our approach trains another neural network to approximate the latent dynamics on the space of neural state variables. This network is a simple MLP that predicts neural state variables at the next time step from the current neural state variables. We term the learned mapping as neural latent dynamics. With the neural latent dynamics, we can now define a more general stability metric as the distance between two quantities. Say we have two predicted image pairs at t and t plus dt. The first quantity can be calculated by projecting the predicted image at t plus dt into its corresponding neural state variable. The second quantity can be calculated by first projecting the predicted image at t into its neural state variable, and using the neural latent dynamics mapping to predict its next neural state variable. Intuitively, the distance between these two quantities measures how far the predicted dynamics, reflected by the given predicted sequence, deviates from the reduced system dynamics projected onto the space of neural state variables. Here, we show an example evaluation result with our stability metric based on neural state variables. This metric also produces patterns that highly match with the metric where we know how to extract physical variables. The Pearson correlation coefficients between these two metrics for known systems are all above 97%. This novel metric based on neural state variables can help us measure the long-term prediction stability directly from videos without additional prior knowledge of the system. The final property of our neural state variables is that they can help produce robust long-term predictions against the visual perturbations. In particular, we applied three types of visual perturbations on the input video frames during test time with different difficulty levels. First, occlusion aims to simulate camera occlusions by covering a certain portion of the input frames with a randomly generated color square. The area of this square indicates the level of the perturbation. Second, background change aims to simulate background color change by covering a certain portion of the input frame background with a randomly generated color square. The main difference is that this perturbation will not cover the object itself. Third, white noises aims to simulate possible sensor noises by adding random Gaussian noises on the frames with zero mean and different levels of standard deviations. The quantitative results clearly demonstrate the strong robustness of models on the neural state variable space across all levels of perturbations. In summary, in this work, we have proposed an approach solely from video recordings of physical systems to automatically discover the intrinsic dimension, the possible state variables that govern the system dynamics, and their significant properties when being applied to predict long-term future behaviors across a variety of simulated and real-world physical systems. We suggest that our approach could help catalyze the understanding, prediction, and control of increasingly complex systems. For paper, codebase, more qualitative videos of our research, please visit our project website. Thank you.